This is a conversation with Dr. Pavlos Msaouel, genitourinary medical oncologist at MD Anderson Cancer Center in Houston, Texas. Dr. Msaouel is a physician scientist researching, diagnosing, and treating rare kidney cancers. MD Anderson is one of the largest academic centers in the cancer world. The implications of that are substantial, meaning that research is very often requested from and placed there, and they collaborate with large centers all around the world. As a result, a lot of new ways to treat different cancers are driven by ideas that come out of institutions like this. On the medicine side, sometimes it's not just using new drugs, but rather different ways of using existing drugs. They're also experts at and heavily research treatment modalities like radiation and surgery in context of cancer care. And of many new drugs, the first time some of these compounds are ever used in humans happen at and are studied at MD Anderson. Knowing this context gives way to understanding why the ideas that are coming from this institution are coming from this institution. Some of these ideas ponder on the question of methodology. Are some cancers as rare as we originally thought? Why do some of these cancers develop in some people but not others? And are the benefits of the clinical frameworks that are currently in place sufficient to accurately diagnose and treat patients with a balanced downside risk? Is there a way to better match patients with the treatment that they need at their current stage of disease? And is the statement, "we need more data," a true statement, knowing that the larger the sample size is, the narrower the confidence interval, which could then drive us further from the truth, something that does have a balance into the realm of subjectivity? You were a singer in a heavy metal band. Then you proceeded to get 2 doctoral degrees, crossed the ocean to another continent, did your medical training, and then moved halfway across that country to do a fellowship. And now you are one of the leading physician scientists at one of the largest cancer centers in the world. What in your heart brought you to this point in life?
It's definitely not something that was pre-planned, and you actually do follow your heart. You follow what you like, and where things will take you from there. And for example, I was always interested in science fiction and, new ideas and new concepts, comic books. I was always a nerd, no doubt about that. And that also connected with heavy metal as a music, an interesting, unique form of art with a lot of people from all kinds of shapes and sizes, interesting people with interesting ideas that are diverse. And that was, something that facilitated my growth as a person. Along these lines, in a similar fashion, there was this duality as well, with the interest in science from different aspects. Clinical medicine, which is the MD degree that I have, and basic science, laboratory medicine, which is the PhD degree. And again, how do you synthesize these two different fields in a way that can help patients?
And in that vein, can you tell me about the system of cancer research that we have here in the United States, Europe, and in other places around the world? How is it done? And why do we have the system in place that we do?
So I would say that a major reason why I actually moved to the United States, which I did not originally intend at all. Oh, okay. I intended to live in Greece, stay in Greece. I loved my home country, and I still absolutely love Greece. But the reason why I moved to the United States was this diversity. So the US system can facilitate the growth of ideas, the interaction of ideas, and this synthesis that I think is very, very important to move things forward. And so, yes, there is obviously structure in the United States system. We have, for example, the FDA that regulates how certain products come to the market, etc. But at the same time, there is flexibility. The FDA, for example, doesn't tell you you have to use this drug, to its specific patients. It does provide the flexibility to choose alongside with your patient based on their unique situation, goals, and values. And this is something that I very much appreciate about the system here.
Can you tell me more about how a drug gets that FDA approval and what are the different levels of approval and why we've been able to establish that system that we do specifically for cancer? Because I think some of the non-clinical people watching won't necessarily realize that cancer really is a separate, different version, and there are some special designations that you wouldn't necessarily see in other branches of medicine.
There are different levels of evidence that apply depending on the type of therapy and as well depending on the type and how common a cancer is. So, for example, if you are interested in getting a drug into approval, that might be a separate process than if you're interested in getting approval for a new diagnostic technique to diagnose a certain cancer earlier or more efficiently. And along these same lines, the level of evidence that is necessary can change depending on the cancer type, as I mentioned. So, for example, for the more common cancers where you need robust evidence that can apply across different scenarios in that same cancer, you may want evidence from randomized control trials. Those are the big trials whereby you have a control, the standard therapy, and then you have the new therapy that you want to test. And through a process like the flip of a coin, it is chosen which therapy patients will receive. That's the random part. And this allows us to quantify what the uncertainty about the differences between the two therapies, the new treatment and the control. And through that, we get these statistical outputs that say, oh, I can claim with this certainty, this confidence that the new therapy is better or the same or sometimes worse than the control. And that is taken into account during regulatory decisions. Outcomes in this sense are also important. So, for example, you're interested in improving outcomes that are important to patients. So, for example, in cancer, survival is an important outcome. Patients want to survive longer, but also patients also want to be cured. So not just surviving longer, but ideally not having cancer. But at the same time, side effects is also something that is becoming more and more important in these considerations and these deliberations, because you want to live longer, but you also want to live well, to have good quality of life. And the other aspects, along with making sure that we use outcomes that are valuable to patients, is also, as I said, for certain types of cancer that may be more rare and more homogeneous in the sense that they're more similar, more driven by specific pathways, there is the flexibility of obtaining regulatory approval without doing this type of randomized trials. First of all, because it's not feasible. Second of all, because it's not needed, and because you have, in this case, a homogeneous population. So the robustness in quantifying that type of uncertainty in more heterogeneous, more different populations is not necessary. What you want is what we call relevance. Relevance to specific patient and the specific rare cancer. And so if you have a biologically well-defined target and you use a drug, and this can be a drug that is not being tested now through the randomized trial, but it's through potentially a trial that will test this drug in patients who no longer have any other options. And you use this drug and you see that patients that were going to die otherwise now have shrinkage of their cancer, remarkable shrinkage, and they survive longer than they would have otherwise. If you see such results, again, there is the flexibility of obtaining approval, and that makes a difference. Again, there is this value of approaching a topic through different lenses and different views and being eclectic in the sense that depending on the problem at hand, you choose the right tools for the job. You choose what is the most reasonable way to test whether this drug or this approach or this therapy should be approved or not.
There was an article that I described in an earlier video on this channel, and it was written by the New York Times back around 2010. So it was one of the old BRAF targeted therapies for melanoma, and it was a placebo-controlled trial. And in that article, they wrote about whether or not it was ethical as the control to have a placebo, which would be no therapy at all. And that's because that was the European standard of care, whereas at the time in America, we probably had IL-2, interleukin. And so the fact that they did the placebo-controlled based on European standard of care, but did that trial here in the United States, does that create a situation whereby we might have a trade-off to say, if we rectify that issue 10, 15, 20 years down the line, because we rectified it a certain way, that's now created a twist in the system that the issues and the trade-offs that come from that twist would then expose itself, and then people would then want to swing the pendulum back so that maybe a generation from now, we now have a same situation where we're doing basically nothing for the patient and comparing it to some active comparator that we think might work, but we don't actually know at that time if it does. I wanted to put a correction here. The trial I refer to is the BRIM-3 trial, and I incorrectly said placebo as the comparator. There was an active comparator. It was dacarbazine, a chemotherapy that's typically not used in the setting of melanoma anymore, at least in the United States. And it really had a poor overall survival compared to today's standards, but also back then as well.
Yeah, and as you very well said, it is always a trade-off, and it is dependent on context. I don't think that there is a one-size-fits-all rule for every situation, or even for every society and every country. Randomized clinical trials are experiments, and in that sense, they share a lot of commonalities, a lot of things in common with how we do experiments in my lab, for example. The key thing about randomized controlled trials is what we call their internal validity. They have to be very well controlled, very well defined. So to give you an example, when we do experiments in the lab, let's say in mice, for example, we don't just select representative members of the mouse species randomly and take them and do the experiments. We use very well-defined animals, potentially genetically modified, very well controlled, and do those experiments. The same, counterintuitively, applies in randomized trials. It was actually the same person who invented randomized trials, Ronald Fisher, is the pioneer of experimental design in biology as well. And that same principle that randomized trials are actually very often not supposed to be representative of a population because they have to be so tightly controlled. And that means that when you design the trial, you design it to answer a specific causal, we call it, question. And that question is actually comparative. You are comparing one thing versus the other. And so depending on the causal question, you might choose different controls. Now, the important thing here, and that has to do with the representativeness, is that because the randomized trials, through that process of randomly assigning the treatment by essentially flipping a coin, give you uncertainty estimates about the comparisons, the treatment differences. They do not give you uncertainty estimates about what's going to happen in the outside population, in the general population. They're not supposed to do that. You could do that if you randomly sampled from the population and then you randomly assigned. But in oncology, and I believe probably in medicine in general as well, we never do that, because instead of randomly sampling, we take a highly selected population of patients, a convenience sample, we call it, who go to centers that have the trials and that will consent to these therapies. You cannot force a patient, randomly to be enrolled in a trial. This is why, in order to transport the knowledge that you gain from randomized clinical trials in the same way that we transport knowledge that happens from any experiments, you have to use different principles than just simple generalizability. You actually need to think, what are the mechanisms that generated the data that we're seeing in the trial based on the conditions of that experiment, based on the controls, and then say, are these mechanisms relevant to the patient that I'm seeing in my clinic, whether I'm in Europe or in the United States or whatever? Are they relevant? And one of the things that we have been advocating for is ways to explicitly represent these considerations. In medicine, medical doctors often do these things implicitly, sometimes more often actually using their intuition. But intuition alone can fail us. And so there are ways through which we can explicitly represent these causal mechanisms and then say, are they applicable to this population or to another population? And in fact, to do that, we have been harnessing knowledge that was generated from the field of computer science and epidemiology.
This is a perfect segue into the next thing I wanted to ask you. We recently did a video with Katie Coleman, and she had a kidney cancer that was so rare in medical literature, says it doesn't even exist at all. It's not supposed to be metastatic. Oncocytoma is fine, but the fact that it spread to her liver was something that's simply unheard of. And even some of the articles themselves, I think there was a poster presentation that said it's academic access, right? That's thinking a little too much about a problem that might not actually be, but for her case, it actually was. What people may not know was that that second treatment was inferred by you. Now, how did you come across that inference based on what you had just described to me?
That's exactly it. You're exactly right. The challenge in that case was, how do we transport information, knowledge that was already existing in order to help this particular patient in this situation? Katie was in a conundrum. What do I do?
Right. And the one thing is, the original treatment that was proposed to her was a 2-medicine combination that may not have been appropriate for her kidney cancer, just to give some context. But then you decided that the treatment for her was that TKI, tyrosine kinase inhibitor, and just monotherapy, and hopefully there should be a response based on the inference from the similarities with chromophobe versus her metastatic oncocytoma. Can you tell me more about that?
And this is exactly that consideration whereby you want to maximize the odds of success for a particular patient while ensuring that you do not cause harm. And so how do you do that? So you think again about what is the putative biology, what is the underlying mechanisms that are driving her particular cancer. And you then think, okay, based on what I know, because nothing is ever just comes out of nowhere. We all built based on contextual knowledge, and we try to use that knowledge to advance science or to navigate the world around us. And so based on that, our understanding of the mechanisms that plausibly would drive that cancer, the combination with immunotherapy would probably not give added value. And so giving immunotherapy would carry risks, side effects that could potentially even delay future surgery, even make it impossible, without having enough rationale for working in that particular case. On the other hand, even though I have to say we still don't have drugs, targeted drugs, that would be tailored specifically for chromophobe kidney cancer or metastatic oncocytoma, which share these features that are of interest to us, still, drugs like a targeted tyrosine kinase inhibitor at least had a reasonable shot. So it's not, oh, I'm desperate, I don't know what to do. It's very easy for people to say, oh, this is a rare cancer, there is no information, I don't know what to do. You can actually flip the narrative and say the way we did with Katie, and say, no, it's a rare cancer that appears to be behaving in a very standard way. And it is the idea, at least in kidney cancer, that you can have the most common kidney cancer, which is clear cell kidney cancer. 75% around of all kidney cancer cases are clear cell kidney cancer. And that is the phenotype. That is what that cancer is. But you get to that cancer through many different pathways, many different mechanisms that converge into that cancer. But under the hood, there are different mechanisms that drive it. And because there are these different mechanisms, that's why sometimes treatments may not work for some, even though they supposedly have the same kidney cancer, and not for others. In fact, the diversity of these mechanisms may be the reason why this is a much more common cancer. But when you have a very, very rare situation that is, for many, it's not even supposed to exist, like an oncocytoma, more likely than not, at least again in kidney cancer, not necessarily in every situation, there may be just a single very narrow way through which it can happen. And that's probably why it's so rare. You have to be like a convergence of a lot of events in order to get something so rare. But because under the hood, that is the pathway, let's say, associated with how the cells breathe. That's what we call, the mitochondria metabolism, which is what we were thinking of targeting in that therapy. Because of that convergence in that pathway, that may actually be why in the extremely rare cases that you do see an oncocytoma spread, it does appear to behave similarly. It goes to the liver. It likes the liver, but then it doesn't like to go to other places. And that is counterintuitive to many oncologists, because very often if a cancer has spread to the liver, it will have spread to many other organs, which in many cases, this is a death sentence. But in this particular case, because of the very distinct and unique biology, spreading to the liver was not necessarily a death sentence. And you can extrapolate that only if you think about mechanisms and biology. I mean, at the end of the day, we move science through hunches, and intuition. And I think that it's generally a good idea to at least intellectually follow those intuitive thoughts, at least initially, and see where they take you. And so, and that is the value again of diversity in opinions. It's not a good idea in general to just shut down the opinions of others and say, what you're saying is, nonsense and biased and whatever. Even if it is biased, it's a good idea to listen to what people have to say and then think, okay, they're making these observations. And are there plausible mechanisms that would indeed be compatible with these ideas, these observations, these hypotheses? And are there ways to try and refute them? The key aspect here is that it is much more valuable as a strategy in science to try and refute hypotheses and ideas and mechanisms than try to confirm them. There are many, many different ways through which something can be confirmed, and you can always find excuses to confirm it. But refuting it, being mistaken, is very, very informative. And so I very much always like, and this is how we made the connection with the high-intensity exercise and renal medullary carcinoma, which initially we thought we were crazy and we're still open-minded. It may still end up that we're wrong about it. But there were patient advocates that were specifically telling us, hey, we're seeing too many folks that have renal medullary carcinoma that are athletic, and that is weird. They had this hunch that something is off. And we also, as time went by, said, yeah, that is worth exploring. And how did we explore it? By taking into account mechanisms and developing studies that could refute those mechanisms. In fact, it was that challenge that led us to this framework and this whole field, as I mentioned, in computer science and epidemiology and now statistics, etc., that explicitly allows you to represent those mechanisms and try to refute them in a coherent, principled, structured way.
All right, what can you tell me about abstract models being different from reality itself?
All models are wrong, but some are useful. And this is true because even if we assume, and many of us do, that there is an objective reality, which means that, if I am looking at the moon, it exists, and then when I stop looking at the moon, it still exists. It exists regardless of whether I'm looking at it or not. That's an objective reality. That's a truth, let's say, some objective truth. But at the end of the day, everything that I experience or I model is subjective. We do not have access to this objective truth. We do not have direct access to the objective truth. And so there is always a model of our truth that will always have some distance from it. It's inevitable. And what happens is that in some cases, those models are useful and they help us navigate the world around us. And in other cases, they are nonsense. But it's not like, because the models are subjective, they will always be subjective. They're not useful. They can be helpful in allowing us to navigate the world. And that is the connection as well with maps. And maps are models of the world, of the terrain. And sometimes you may choose in those models to highlight certain things. For example, you may want in this map to highlight, wildlife, or, the altitude differences, or COVID incidents if you want to avoid it. And so you change the resolution and your model depending on what your purpose is.
So we had mentioned trade-offs earlier, and sometimes I wonder if developing models in itself is a trade-off, because they're not reality itself, and only some of them are useful. And so in essence, you would be putting a lot of entropy in the system. You're adding a lot of chaos into the universe by trying to recreate the universe. And so this trade-off has been described multiple times, and you see it every day when you see patients. Can you tell me more about this?
Yeah, and this trade-off, which is called the Bias-Variance trade-off, is what I would call the first law of data analysis, in the sense that essentially this trade-off is inevitable. And Xiaoli Meng and Kelly Liu actually recast this trade-off in medicine, a specific version of this trade-off, as the patient relevance and robustness trade-off. And what is relevance? So relevance is, how does this model apply to a specific patient? How true is this inference from this model for a specific patient? Is it relevant for a patient? And then robustness is, if I change the conditions for a patient, so if it's not the same patient, but different patients, similar, but not exactly the same, how much do my inferences apply to this group of patients? How robust are they? How close are these inferences, and how much do they contain knowledge about the whole population? There's always a trade-off, because the more you think about the particular situation of a specific patient, the less that those conditions apply in more generally, because every single patient is unique. Every single patient in reality has the most rare disease in the world. Only they have it if you go extremely deeply into it. And so what you always want to do is to balance this trade-off, because this relevance and robustness. And in fact, this same trade-off applies when you think about statistical models. And so, for example, there are at least two big schools of statistical modeling. The first one is called the Bayesian modeling, and the other one is called the classical or frequentist modeling. And they very nicely can be mapped into this trade-off. You cannot have one without the other. They're actually two sides of the same coin. And people get very opinionated that, especially in the 20th century, Bayesian inference is the best and frequentist is useless, or the opposite. No, they're both useful, because they both can be used to help you map within the relevance-robustness trade-off. So the extreme version of Bayesianism, which is called subjective Bayesianism, takes into account everything that you know about a specific patient or a specific situation. And essentially what it allows you to do, if you knew everything, which you never do, it allows you to create in your mind perfect copies of the same patient, and then forecast, okay, if I do X, what is going to happen versus if I do something else. It's impossible to do this perfectly, but that's the thing. These are theoretical systems. Because of this ability, this is why subjective Bayesianism is a very good system for making bets. In fact, it was developed to win bets in gambling. And if you think about it, whenever we make decisions about a specific patient in the clinic, we're actually trying to bet in their favor. We want to maximize the odds that they get the best outcome. But at the same time, on the other extreme is what we call pure randomization, where you randomly sample and you randomly assign a treatment, which you can never do for a specific patient. But if you could do that for a population, you could reliably quantify the uncertainty statistically about those inferences for that population. That's a brilliant concept. So frequentism, when it evolved in the middle of the 20th century, was a brilliant idea. And so what we want is both to have this coherent decision making that Bayesianism allows you for specific patients, with the robustness, what we call sometimes in forecasting calibration, that the frequentist approach provides. And so finding that fine balance is the holy grail of data modeling and clinical decision making as well.
When it comes to Bayesian, I remember coming across it a long time ago on my own with a video game called World of Warcraft. And in there, I had a character whose class was a warrior. And it really relied on a critical hit rate. And the higher you could get the critical hit rate, the better. But then I started realizing that particular class of character at the time, 2004, 2005, playing that game, you could reasonably only get maybe 3 hits on your opponent before that's it. It's over, right? If you don't get those 3 hits, you're done and you lose. But if, say, your critical hit percentage is 35%, in all of the populations of the encounters where you get 3 hits, how many of those are 2 of them critical hits, and how many are all 3 critical hits? And so I think in terms of what's meant by Bayesian in the patient sense is, given any patient who comes in next, what's the probability that they would respond to one treatment over the other? Is that a correct assessment?
Yeah, and that connects back to, when we were discussing before about our origins and how myself, I'm clearly a nerd, interested in things like heavy metal, science fiction, etc., and definitely computer games in the past. And I think the bow tie itself signifies my nerdiness. And what you said is very true, that in video games, being knowing that video games have a certain structure. The rules of the game are there and they're open. That's a little bit different than how the outside world is, where the way the world works is still unknown to us. But because the mechanics of video games are more often than not known, we can actually use Bayesian approaches indeed to make coherent inferences. And that is the value of Bayesian approaches, that indeed you can make coherent inferences based on prior information and my prior understanding. I can forecast that this is going to happen if I do X, Y, and Z. Absolutely. And I think that there is definitely a connection there. And we do that with patients, whereby, again, whenever we see an individual patient, we are trying to make coherent inferences and decisions with them, incorporating their goals and values, because the subjective trade-offs that are quantified by their goals or represented by their goals and values can actually change the decisions. And there can be no decision without such subjective trade-offs on risks and benefits and what you're interested in achieving. Once we know that from the patients, together with the patients, we make coherent decisions. And the way we make them is we try to make the decisions that maximize the odds that we're going to get the outcome that we want. And so in that sense, we want to succeed. But at the same time, here is the complementary aspect. We also want to make sure that in the long run, as we are using a certain framework. Like, let's say I have a model that predicts what's going to happen to the patient I'm seeing in clinic. And I'm using that model to maximize the odds that they're going to get a good outcome. But I want to calibrate my model and see how it behaves in the long run. So the way to do this is you aggregate the data. So it needs a lot of hard work, but that's the fun part of science. You look at the data and you say, I expected this outcome to happen, and it happened, which is great for the patient, but we actually learn less when you are correct, because you have your model and your model is correct. But if we get a different outcome and our model is proven to be off in some aspect, doesn't have to be completely off, then by those mistakes, we learn and recalibrate, and improve our models. And then the next time we are tasked with making, again, inferences and decisions to help our patients, we're better at it.
So you're telling me in this bias-variance trade-off that the more you try to make a specific measurement in a patient's case, for example, not, measuring with a tape or anything, but we're dealing with life and death situations here, the more you try to make a specific measurement, are you further away from the actual truth from that measurement?
Only if you are interested in a truth that may apply to a population. The deeper you go into understanding a patient, the more closer you get to the truth that applies to that patient, but not necessarily to a group of people. And that is the difference as well between reproducibility and robustness. So if you're doing an experiment that is not reproducible, then under the same conditions, exact same conditions, you get different results. So this is noise. But if you get certain results under certain conditions, and then you change the conditions just a little bit, and that could correspond to a little bit of a different patient, and now your results do not apply, then your results are not robust. Whereas if you change quite a lot the conditions, and yet you get the same results, the same inferences, then you have a lot of robustness. But the thing is that the deeper you go, the more specific you go into something, the less likely it is to apply to different conditions, different contexts. It's not always the same balance. So sometimes in certain situations, you can have very, very high patient relevance and very, very high robustness. These situations are what we call deterministic. And they're very mechanic, very high signal to noise ratio. But in medicine, in the vast majority of cases, our decisions and inferences are not deterministic. They're actually what we call stochastic or probabilistic. They're based a lot on probabilities because there is less signal to noise ratio. And so in those cases, we have to find the right balance between relevance and robustness. And what happens to connect with the situation in rare cancers, common cancers that tend to be heterogeneous, different, require a lot of robustness. And that is why they benefit from randomized trials that allows you to quantify the uncertainty about, your inferences and have these robust inferences. But more rare situations that hopefully, not always, but they tend to be more homogeneous, they allow you, if you go deep enough into the mechanisms, the biology and other considerations, to make relevant inferences for these rare populations. And so that means that, again, in the same way that we cannot just take the extreme position, Bayesianism is the best and everything else is useless, or the opposite. In the same way, we cannot take the extreme position and say, oh, we can only make reliable inferences for common diseases, or the opposite. It's always a balance. And once you think in this way, you get away from this hopeless situation whereby the disease is considered rare, you cannot do a randomized trial, so we're done. We cannot make inferences, and that's it, go away. No, if you start thinking along these lines, you can actually create science and a framework and approaches to help patients with rare diseases. And in fact, then you can apply these approaches to individualize potentially the care also of patients with common diseases.
So you recently wrote a paper about something called the big data paradox. Was the phrase coined by you? And can you tell me a little bit more about what it is?
Definitely was not coined by me. And in fact, the big data paradox has been known since at least the middle of the 20th century, it just didn't have that name. It is essentially a consequence of the bias-variance trade-off, or in the case of medicine, the relevance-robustness trade-off. And what this consequence is that because of this trade-off, what happens is that if you have, let's say, a clinical trial, and you get from this clinical trial certain results that have confidence intervals to assess, to quantify the uncertainty about these results. The question that we can ask is, okay, if we doubled the sample size from that clinical trial, or tripled, or whatever, there is no catch here. This applies to everything. This is a general principle. This is the first law of data analysis. You double the sample size, or you triple the sample size, or whatever. And you keep the same population, same conditions, everything else the same. The probability that those confidence intervals, the uncertainty estimates, the statistical outputs that you get from the trial now that you doubled the sample size or tripled the sample size, contain the truth, the actual truth that you're looking for, actually decreases. And so many people will think that it increases, or that at the very least it stays the same. It's very counterintuitive why the probability that now the confidence interval will contain the truth decreases. And the reason is that as you increase the sample size, the confidence intervals, or the standard error, are a function of the sample size. So the higher the sample size, the more they will narrow. And since your model is already away from the truth, by definition, it's a model, with lower sample size and wider confidence intervals, they're going to be more likely to contain the truth. But as you narrow them, your model is still in that same coordinate. But the confidence intervals, or the uncertainty estimates, the standard errors, will narrow and now will not contain the truth. And that is something we always have to keep in mind, because it is a consequence of the trade-off. In order for me, for a study to actually contain the truth, if you increase the sample size, you have to make sure that the study remains relevant to the question at hand. That's the point of relevance. You have to decrease the bias if you can. And how would you do that? The one for initial consideration, key consideration, is you need to maintain data quality, because it doesn't always happen, but very often it does, that the bigger the studies, the lower the quality of the data. And that happens a lot with especially observational studies. It's not just experiments. It's every study is susceptible to this paradox. And so very large studies can be hindered by poor quality of the data. So we have to make sure that we maintain data quality. The other thing that we have to make sure as we increase the sample size, and that is key, is that we accordingly potentially change and improve our model to account for this heterogeneity of the patients that you're enrolling and that may require adapting the model and learning more as you go. The third way that we can account for this paradox is by, instead of just making the confidence intervals and the standard error that are a function of the sample size, use intervals or metrics that take into account not just the sample size or the robustness, but also the relevance, the bias, not just the variance. And as I mentioned, this was largely known since at least the middle of the 20th century, but it became a big problem now in our era because we have big data. And the first time this was coined as the big data paradox, before it was just known as a consequence of the bias-variance trade-off, was by Xiaoli Meng when he used it to explain, at least in part, why the forecasting of the 2016 US elections was off. And at the time, we had tons of big data related to that forecasting, and yet the predictions were off. And at least in part, this was because of the big data paradox. The more data we had, the more surely we would fool ourselves. And the next big situation where the big data paradox declared itself was more recently with a paper published by Xiaoli Meng and others, a fantastic paper published in Nature, where what they did is they showed that if you wanted to predict the uptake of the COVID-19 vaccine after it got approved in the United States, you wanted to predict, okay, how many people are actually going to use this vaccine? And for that, you have as your gold metric the actual data of the people from the CDC that actually used the vaccine. And you have then various health surveys that were used to predict what would have happened. And remarkably, there was a health survey by Facebook Delphi, which is the largest health survey conducted in the United States to date, with 250,000 people. And in that survey, the predictions of COVID-19 vaccine uptake were completely off because of the big data paradox. Whereas another survey with just 1,000 patients that was more well-structured, more relevant, and was more able to accurately forecast the COVID-19 vaccine uptake. The 250,000 survey was completely off. The 1,000 people survey was almost consistently right on with its predictions. And this is probably the reason why all these big data companies and endeavors and etc. are not going to conquer the world anytime soon.
Can you tell me a little bit more about how does this big data paradox fit in with Katie's case?
The big data paradox absolutely fits with Katie's case because the reason why people would be desperate or freeze when they think, oh, how am I going to treat a rare cancer, is because they believe that the bigger the data, the more likely we are to make correct inferences. But once you start framing this in the correct way through the relevance-robustness trade-off, then you can actually flip the narrative and make it so that we can make coherent, reliable inferences and decisions for patients with rare cancers, including ultra rare cancers like Katie's.
Got it. This really reminds me of a lot of toxicology studies because you have other branches of medicine where you have 100,000 patients on a trial, right? Then you have oncology studies where it could be a couple hundred patients in a trial. And then you have rare poisonings where sometimes even when they happen, you might not even remember that you're participating in a trial. And because you're so concerned about treating that one patient at that particular point in time. And a lot of times the antidotes, so to say, for the treatment are mechanistic based. You have to think about what's actually happening to the patient rather than we don't have data on 7,000 poisonings of a particular kind in certain instances, right? So you just have to understand kind of the basic science and the chemistry and the toxicology of what's happening. So there is a little bit of applicability in my case here.
Oh, in fact, whenever you're so right about that connection, because whenever we describe this framework and these paradoxes, it is actually folks that are interested in toxicology that immediately see the connections. Also, people that work on bioassay development, because these concepts like calibration, robustness, etc., are directly connected with what they do. So a lot of folks that focus on biochemistry, chemistry, physics as well, are very much on that same wavelength, and by using even this terminology and this framework, it actually facilitates a dialogue between people that do something seemingly completely different, which is clinical inferences and clinical decisions, with folks that, work on the more basic sciences like chemistry, biochemistry, toxicology, even particle physics.
And we can even go into economists, right? And people who forecast prices and stock traders, and all the information that they have in the past will still not tell them what happens tomorrow. Or even people who bet on sports games, right?
And in fact, even within the economics field, as far as I know, there are these divisions between folks that think this in a different resolution, the macroeconomics and the more micro, and whereby they focus on doing even experiments to understand the mechanisms that inform certain decisions by populations or by groups. And it is indeed through the integration of knowledge from these different aspects of economics that you could improve your forecasting models.
So in the paper, you have a diagram showing the truth and how the larger the sample size is, the narrower the confidence intervals, therefore you might be getting further away from the truth. My question is, what happens if the truth is so large that it encompasses those confidence intervals? The analogy that I was thinking of immediately when I saw that image was the three blind men touching the elephant. One touches the trunk, the other touches the side, the other touches the ears, and they all describe the same elephant in very different ways. However, it does relate back to the same elephant. So the question formally would be, how would you account for the subjectivity in the truth and the interpretation of the truth, knowing that in a couple hundred years, someone's going to reinterpret the truth into something completely different and try to burn down the framework of everyone that came before them for the last several hundred years?
Yeah, and this question relates to the fact that our understanding of the truth, whether there is an objective truth or not, will always be subjective. And that is actually a strength. Every system, including the Bayesian and frequentist models that I mentioned before, they are by definition subjective. They have this subjectivity. But what you alluded to with the example of the elephant is a key concept of triangulation, of trying to arrive to the truth through different orthogonal ways. And that is absolutely important. We use this principle in the lab where we design different experiments that try to uncover the same truth. Because if you see those results pointing to a certain mechanism with one experiment, but then you do a different orthogonal experiment and then you get something completely different, that is a problem. You want experiments to converge to the same mechanism. Now, when I said that's a problem, that is also actually useful because every time that our experiments, and that happens a lot, don't come out the way we want, we actually learn even more from them. Again, you learn from your mistakes, but triangulation is important both for the lab and even in the clinic. That is why it's so important that we look at data through different ways, through different lenses, trying to arrive to the truth.
So how should we address the problems that are created by this big data paradox?
And this is something that we've been thinking about a lot, because if we address these challenges and reframe them again as a strength, then we can actually improve the care of our patients. And so having a lot of data is actually a good thing, as long as we make sure that they're high quality data and that we understand their origin, their history, how they were generated, what are the mechanisms that generated them, and how do they apply across diverse situations and populations of patients. And so we have been very interested along these lines in not just focusing on a purely data-driven approach. There are these data-driven approaches that just use data without thinking about the mechanisms that generated them that have been quite successful. This alludes to the use of AI. A lot of these deep learning approaches that have been fantastic in moving science and even aspects of medicine forward are very useful in situations with high signal to noise ratio. However, when you get into this more stochastic type of forecasting, they may not necessarily work that well for informing patient care. On the other hand, we have these model-based approaches that take into account mechanisms that generate the data. And the question is, can we integrate these two approaches together and create a hybrid approach that takes the strengths of both and addresses the big data paradox and informs in a more powerful way patient care? We believe that this is a fruitful strategy and we're exploring it. And there are others as well that are also arriving to that same conclusion. I was reading an article that was talking exactly about the value of this hybrid culture of data analysis, and that when you start seeing things through this lens, actually that dichotomy, once again, there is the complementarity, the dichotomy dissolves between data-driven approaches and model-based approaches. Another article, again, I was reading called this centaur AI from the Greek word kendavros, which was this creature that was a fusion between a human and an animal, a horse. And how when we create these hybrid approaches, we can actually make powerful models that address both the big data paradox and are more able to generate tailored inferences for the patients that we care for in clinic.
What's interesting to me is when you talk about the duality, right? You have bias versus variance, right? And even in something simple like cameras and lighting. You have lights, but you need to have shadows also. You cannot just unanimously have one. And so old cultures, right, or ancient cultures like the Greeks knew of those concepts. Even the ancient Chinese knew of yin and yang, right? And so to be able to understand that if you swing in one way, in one direction, inevitably that pendulum will swing back in another direction. I came across a recent Twitter spat with a YouTube friend of mine, and he's a cardiologist in the UK. It wasn't a huge spat, but there was a iceberg diagram that was produced by one of your colleagues at your institution. And when I saw that, it generated some controversy on Twitter, understandably so, I think, in my opinion. The thing is, to me, I see that as confirmation of all the ideas coming out of your institution, especially knowing you and knowing your publication on the big data paradox. Based on the negative reaction that I got, I saw some positive reaction too. Knowing that you develop these ideas stemming from your institution that sees rare cancers, how do you win the hearts of more general practitioners in the sense that they do see complex polygenic diseases?
Well, first of all, I think that if you create controversy with something, a concept like, let's say, the iceberg figure, which I really enjoyed and I love that figure, that's a good thing because it means that you've stirred the pot and you're making people think. And not only that, the reactions, the negative reactions, are themselves very useful because you have people who are seeing things through their lens, and that typically is the lens of thinking in the terms of variance or robustness, which is a very important one. It's again that complementarity and that duality of approaching a concept. So you can actually understand a phenomenon better when you look at both of its complementary properties. It's kind of like, as you mentioned, the light and dark, or, the bias and variance trade-off, or the relevance-robustness trade-off. I've thought about what you asked about why a lot of the individualized and relevance-related approaches that do come from our overarching group and an institution. And that alludes to also the fact that our institution has been at the forefront in pioneering Bayesian methods. And that makes the connection with what we discussed exactly before, Bayesian clinical trials. And our statisticians and physicians, way before I came to the institution, way before, were pushing for these approaches at a time when people thought that they are nonsense. And that again has to do with having this lens of individualizing patient care. And one of the things that happened is that in fact, when I came to MD Anderson, I was a hardcore Bayesian myself. So I was seeing things through that pure lens. And as I got immersed more and more into that approach, I started to understand its limitations as well. And I started to realize that only by integrating these different perspectives, you can actually create things that work and help patients. And I think that nobody can refuse that what Vivek is doing is actually helping patients with rare cancers. He's done such a remarkable work in getting drugs to approval for patients and cancers that used to be a death sentence. That's a thing, period. Now, when you look at what he illustrates as below the surface of the iceberg, most of the things that he highlights are things related to relevance. And of course, there are going to be people that are going to be less interested in that view. And in many ways, you don't necessarily have to convince everyone. We have to keep that dialogue open because none of us has the perfect answer. Far from it.
Dr. Msaouel, thank you so much. Where can people find you?
On Twitter. And they can find me. I work at MD Anderson as a clinician seeing patients with kidney cancer, specializing in rare kidney cancers, running clinical trials for kidney cancers, and also in my lab, whereby we do research in animal models and cell line models to find new therapies for kidney cancers and understand why certain kidney cancers happen to certain individuals.
Thank you so much.
Thank you. Thank you for having me.